Every year, over 4 billion miles of fiber optic cables are produced worldwide. That's enough to wrap around the Earth more than 160 times. But few people know that their journey begins with sand. A special kind, whose purity is measured in parts per million. Because even one microcrack can destroy a signal that's racing for thousands of miles at the speed of light. What is this magic? How does ordinary sand turn into transparent threads, thinner than a hair, but stronger than steel? Watch closely. At the end of this video, you'll learn a secret you've never heard before. To create a thread capable of transmitting light at a speed of over 186,000 miles per second, you have to start with sand. But not just any sand, only special, extremely pure quartz sand, where the main substance is silicon dioxide. For fiber optic production, sand with a silica content of over 99.9% is used, which means in 1 million parts, there's only 1 part of impurities. Imagine this. In every pound of raw material, no more than a few millionths of an ounce of impurities. And this is critical, because even 1 billionth of an inch of foreign metal or organic matter can cause light scattering or absorption in the fiber optic cable. And then the signal, which was supposed to travel 60 miles without amplification, simply disappears. Raw material for fiber optic cable isn't just washed or filtered, it's purified at the molecular level. Manufacturers often use vapor phase chemistry. Quartz sand is converted into gaseous silicon tetrachloride, which is then distilled, filtered, and deposited as pure vapor. And only then is it converted back into glass. Add to this strict control of temperature, humidity, and air currents in clean rooms, and you'll get an idea of how far this is from an ordinary sandy beach. Production laboratories look more like National Aeronautics and Space Administration sterile zones than a glass workshop, and all for the sake of ensuring there's not a single defect in every yard of the future fiber. Because when you're transmitting light over thousands of miles, even one microscratch can cost you signal quality. A large, transparent glass cylinder that will later be melted and drawn into a very thin thread. This is the fiber optic preform. This huge glass rod is made using a method called vapor deposition. In a large furnace, air is mixed with very pure gases. These are different substances that turn into vapor when heated. These vapors hit the inner surface of a transparent tube, which is heated very intensely. When the vapors touch the hot wall of the tube, they deposit and turn into tiny droplets of glass, like dew collecting on leaves in the morning. Gradually, these droplets collect, layer by layer, until a thick layer of glass forms inside the tube. Then this tube is heated even more intensely, and it collapses into a dense solid rod, and this is our preform. The preform is placed in a special furnace that heats up very intensely. The temperature inside it reaches approximately 4,700 degrees Fahrenheit. This temperature is so high that the glass becomes soft and starts to melt, like caramel on a stove. When the end of the preform melts, a drop of molten glass begins to drip from it. This drop is very carefully drawn downwards, and a thin thread is formed from it. This thread, the optical fiber, is drawn at a speed of approximately 1,000 feet per minute. Imagine that. It's faster than a cyclist moving through the city. It's important for the thread to be of uniform thickness throughout its length. The thickness of an optical fiber is usually around 125 microns, or approximately 0.005 inches. That's very, very thin. For comparison, the average human hair is about 100 microns thick or less. To keep this diameter under control, special instruments are used during the process. They look at the thread in real time and measure its thickness. If the thread starts to become thicker or thinner, the system automatically changes the drawing speed or the furnace temperature to correct it. After the optical fiber has been drawn from the preform and has become a thin, transparent thread, it needs to be protected. The fiber is very thin and fragile. If left unprotected, it can easily break, cracks will appear, or dirt will get on it. Therefore, immediately after drawing, the fiber is coated with a special protective layer. A thin thread is pulled from the furnace. After the furnace, the thread immediately goes into a coating machine. This is a special device that clothes the thread in a plastic sheath. The optical fiber enters a special part of the machine called the coating head. It's like a small tube, or nozzle, inside which there's molten protective material. As the fiber passes through this tube, a layer of liquid polymer is evenly applied to it. The polymer has very low viscosity, so that the coating is thin and even, but dense enough to protect the fiber. This coating layer usually consists of two parts. The primary coating is a very soft, elastic layer that dampens mechanical shocks and allows the fiber to bend. The secondary coating is harder and more rigid, protecting against external influences, dust, and scratches. These two layers are applied sequentially, one after the other, to provide reliable protection. After applying the liquid coating, the coated fiber passes through special forming rollers. They regulate the thickness and evenness of the layer, pressing the coating uniformly along the entire length of the fiber. These rollers are very precisely calibrated so that the layer is not too thick or thin. After the polymer has been applied and shaped, the fiber passes through a zone of ultraviolet light. Here, the polymer instantly hardens under the influence of ultraviolet lamps. This is a process called polymerization. Anyone who gets their nails done knows how this happens. Ultraviolet lamps emit light of a specific wavelength that activates chemical reactions in the polymer. Thanks to this, the coating quickly becomes solid, while retaining its elasticity and ability to protect the fiber. This is a very fast process. The coating solidifies in fractions of a second, literally. This method does not heat the fiber, so it doesn't damage it. This provides very strong and durable protection. The entire machine is equipped with sensors and control systems. They constantly measure the coating thickness, fiber feed speed, and uniformity of application. If the coating layer is too thin, or there are defects, the system either stops the process or adjusts the parameters to avoid defects. At the end of all this technological magic, a spooling module, rotating with a hum resembling the sound of a jet engine, only in miniature. The fiber, like transparent silk, lies down smoothly and precisely, coil after coil. It shimmers in the light of the lamps, reflecting cold blue and white hues. The spool moves smoothly, to the left, then to the right, with millimeter precision, as if an artist is painting pictures with movement. One wrong angle, and everything will go haywire, so the system automatically adjusts the rotation speed and fiber tension with surgical precision. Around are sensors, lasers, cameras. They carefully ensure that the fiber lies flat, doesn't twist, and doesn't create tension. With every minute, more and more layers appear on the spool. Imagine, in a few hours, there are already several feet of thin, almost invisible fiber there. And all this without a single break, without a single scratch. Because even a micro crack and the light signal will get messed up, like a radio wave in a storm. Before cable assembly begins, the fiber from the spool is carefully wound onto a production line. Since one cable usually contains several fibers, individual threads are combined into ribbons or modules. For ribbons, the fibers are arranged parallel in a single plane, for example, 12 pieces, and glued together with a special resin. This makes them easier to work with during connection. For bundles, the fibers are twisted into a spiral strand and placed in a plastic tube. These ribbons or bundles are then placed into buffer tubes, thin, flexible plastic channels that provide space for the fiber's slight movements. This is important because when the cable's temperature changes or it's bent, the fiber slightly expands or contracts, and the buffer tube helps prevent it from being damaged. A gel that repels water and absorbs vibrations can also be added inside these tubes. Around the buffer tubes, strengthening elements are added. Fiberglass or Kevlar, very strong threads that protect the cable from stretching. Metal wire, for additional mechanical strength or grounding. A central strength member, a rigid element in the center that maintains the cable's shape. These reinforcements are needed so the cable can withstand tension, impacts, bending, and remain intact for decades. All of this is wrapped in an outer jacket. This is a dense plastic or polyethylene pipe, resistant to ultraviolet light, moisture, rodents, and temperature fluctuations. The cable is tested. The bandwidth of each fiber is checked, as is its bending strength and resistance to moisture. Then it's wound onto large drums, marked, and technical documents are added, and it's ready for transportation and installation. Every year, thousands of tons of fiberglass rebar are produced worldwide, a material that's throwing down the gauntlet to steel. Imagine hundreds of spools of fiberglass, thinner than a human hair, merging into a single river, passing through sticky resin baths, red-hot dyes, and scorching ovens to be born as a rod that's 4 times lighter than steel, twice as strong, and completely immune to rust. This rebar is capable of doubling the lifespan of concrete structures and changing cities forever. But the most interesting part is hidden in the very heart of this process. If you watch until the end, you'll discover a secret that will completely change your understanding of the future of construction. It all begins at one end of a massive workshop, where a structure resembling a giant library for threads stands. This is called a creel. On a wall several yards high, hundreds, and sometimes even thousands, of huge bobbins are installed in neat rows. On each of them is wound the finest glass thread, or roving. This isn't the kind of glass that windows are made of. This is a special fiberglass, produced by melting glass and drawing it through microscopic holes. The result is threads thinner than a human hair, but with incredible tensile strength. These will be our skeleton, our internal army that will give the rod its insane strength. From each of these hundreds of spools, its own separate thread is drawn, and they all come together into one thick, fluffy strand. It's like thousands of small streams merging into one large river. This dry, white strand is the soul of the future rebar. Next, this river of fiberglass begins its journey. It passes through a system of guides and tensioning devices. This is a very important, though inconspicuous, stage. Every one of the thousands of threads must be tensioned with the same force. If one thread sags, while another is too tight, the load in the final product will be distributed unevenly, and it will lose its strength. Therefore, the machine carefully aligns them, preparing them for the most important moment: a baptism in resin. The dry glass strand is slowly submerged into a bath filled with a thick, sticky liquid, similar to honey or syrup. This is a polymer resin, our meat that will grow on the glass skeleton. It's a complex chemical cocktail. The base is usually a polyester, vinyl ester, or epoxy resin. A hardener is added to it, a catalyst that will trigger a chemical reaction and force the liquid to turn into a solid plastic. Various additives can also be added here. Pigments to add color, ultraviolet inhibitors so the rebar isn't afraid of sunlight, and flame retardants for fire resistance. The task of this bath is to saturate every single, even the tiniest fiber. The strand must be completely submerged in this resin so that no dry spots remain. The saturated strand, heavy with sticky resin, exits the bath and heads to its point of birth, the forming die. This is the heart of the whole process. Imagine a thick steel plate with a perfectly round polished hole, the diameter of which exactly matches the diameter of the future rod. The die is heated to a certain temperature. When the wet strand is pulled into this hole, several things happen at once. First, the die, like a press, squeezes out all the excess resin, leaving only the necessary amount. Second, it tightly compresses all the fiberglass strands together, forming a perfectly round rod. Third, the heat from the die initiates the initial stage of the chemical hardening reaction, or polymerization. The resin begins to transform from a liquid into a gel. At the exit of the die, we can already see the familiar shape of the rod, but it is still soft and vulnerable. But how does it get its famous ribbed surface to hold well in concrete? Immediately after exiting the die, while the rod is still hot and soft, a special strand of the same fiberglass is wound around it. A thin, resin-saturated thread is wound in a spiral on the surface of the rod, creating a relief pattern. Sometimes, for even better adhesion, fine quartz sand is sprinkled onto the sticky surface, which adheres permanently to the resin. Now, our rebar has not only strength, but also teeth with which it will hold onto the concrete. The formed and wrapped rod enters the longest part of the machine, the curing tunnel, or polymerization oven. This is a long chamber that can extend for tens of feet, inside which a high temperature is maintained, usually 400 degrees Fahrenheit. Here, the final transformation takes place. This is not just drying. Under the influence of heat, the resin molecules begin to actively bond with each other, forming a strong, rigid three-dimensional network. The liquid, sticky syrup turns into an extremely strong and hard composite material that permanently binds millions of glass fibers into a single monolith. It's like baking a pie. As the rod slowly moves through this hot tunnel, it acquires its final, rock-solid hardness. But what pulls it through this entire long journey, from the spools to the oven? At the end of the line stands a special pulling device, which gives the whole process its name. Usually, it's two caterpillar-like mechanisms, similar to tank tracks, located one above the other. They gently but very firmly clamp the already finished hard rod with their rubber pads and pull it towards themselves at a constant, precisely calibrated speed. It is they that create the force that pulls the fiberglass through the resin bath, through the forming die, and through the oven. The speed of this movement is one of the most important parameters that controls the quality of the final product. And so, from the other end of this long conveyor, an endless, perfectly straight, hard and hot fiberglass rod emerges. The final cord is cutting. An automatic saw is installed across the line. It synchronizes with the speed of the rod's movement, at the right moment makes a quick forward motion, and with a sharp zzzt, cuts a piece of standard length, for example 20 or 40 feet, from the endless ribbon. Then it returns to its starting position, waiting for the next section to arrive. The finished, still warm rods roll onto a cooling table, and then they are collected into bundles, tied, and sent to the warehouse. And just like that, before our eyes, thousands of fragile glass threads and a barrel of sticky liquid, having passed through baths, presses, and ovens, have turned into a lightweight but incredibly strong building material of the future, ready to challenge rust and time in the concrete jungle. The fiberglass rebar market is not yet a giant like the steel market, but it's the coolest and most audacious newcomer at the party, rapidly gaining popularity. The global market for this material is already valued at hundreds of millions of dollars, and the forecasts are just insane. It's expected to grow by 10 or 12% annually. This means that more and more engineers and architects are looking at rusting steel and saying, "Dude, we can do better." And now for the main features that make steel rebar nervously smoke in the corner. The first and most obvious is weight. Fiberglass rebar is about 4 times lighter than steel of the same diameter. Sound boring? Now imagine this in real life. Imagine a truck carrying rebar to a construction site. It can bring 4 times more length of fiberglass rebar in one trip than steel, because it's limited by weight. Or for the same amount, it will take 4 times fewer trips, which saves fuel and time. On the site itself, 2 workers can easily carry whole coils or bundles of fiberglass rods, whereas moving steel requires a crane. This is a colossal saving in logistics and labor. Second is strength. And here, fiberglass just steps into the ring and knocks out steel in the first round. Its tensile strength is about twice as high as that of standard steel rebar. So you understand, to break a fiberglass rod, you need to apply twice as much effort as for a steel one of the same diameter. This means that in some structures, rebar of a smaller diameter can be used, saving even more weight and volume. It's like comparing a regular rope with a climbing rope. At a smaller thickness, it can withstand much greater loads. But the main trump card, the real superpower of fiberglass, is its war against rust. The main enemy of any reinforced concrete structure, from bridges to parking garages, is not the load. It's rust. Water and salts penetrate through micro cracks in the concrete, reach the steel rebar, and it begins to rust. The rust expands in volume and literally tears the concrete apart from the inside. Annually, the US spends billions of dollars on repairing bridges, parking garages, embankments, and tunnels destroyed by rebar corrosion. And fiberglass? It just laughs in the face of rust. It is chemically inert. It is completely indifferent to water, salt, acids, and alkalis. This means that the service life of the structure increases dramatically. A concrete structure reinforced with steel is designed for more than 50 years. And a structure with fiberglass rebar is easily designed for more than 100 years.